we'll get started. It's my pleasure today to introduce Jocelyn Reed. Jocelyn is a Canadian who's been moving to progressively warmer climates as her careers progress.
Sadly.
She did her graduate, she's sad about it. She did her graduate work at the University of Wisconsin-Milwaukee, followed by a postdoc at the AEI near Berlin, and then another postdoc in Mississippi, which I suppose might be almost as warm as where she is now, or warmer. Now she's a professor at Cal State Fullerton with, I guess, a growing and exciting group there of gravitational scientists. Her work has been in various aspects of neutron stars and gravitational wave science, and lately she's done a lot of work on how one might measure the equation of state for neutron stars using gravitational wave observations. So today maybe she'll talk a little bit about that.
Yep. Oh, thank you very much, and thank you very much for inviting me up here. It's very nice to come back to Canada. I sort of realize whenever I'm here all these little tiny things that I've missed living in the States for so long. But yeah, so I'm going to be talking about dense matter, the kind of matter that you find in the core of a neutron star, and where it comes in to influence gravitational waves. So sort of as an overview, I'm going to be talking a little bit about how we model the effects of matter on an in-spiral, the gravitationally wave-driven falling in of two orbiting compact objects, and the characteristic parameters we can use to describe what affects the waveform that this kind of thing produces, how we detect and estimate the parameters, and this is actually going to be kind of a big chunk of the talk, but then some of the things I'm going to emphasize as sort of main points are how we think about the systematic errors in our current types of modeling, the impact of numerical simulation on the merger for this kind of measurement, what the current uncertainties are and how they impact what we can do, and some of the current projects that students at Fullerton are working on. As a caveat, I'm going to be talking almost exclusively about binary neutron stars, since you have a Francois here to talk to you about black hole neutron stars. There's similar effects that I'll talk about that can be seen in the black hole neutron star binary, similar magnitude at the same distance. So I'm focusing more on binary neutron stars because in the particular volume, we expect those to be more numerous, but of course, until we actually measure some rates, all bets are off. So let me get started. Okay, so our objects of interest here are neutron stars, which are things where you take something that is more massive than our sun and compress it down to a size that is apparently between Toronto and North York. So we have here a very extremely dense object, something where the average density is denser than the nucleus of an atom. And we observe these in various astrophysical senses as radio pulsars, as accreting objects bursting in X-rays. But typically, it's very difficult to see exactly how big something this tiny is when it's astrophysically far away. So the kind of size, characteristic size of a neutron star remains fairly uncertain. This 10 to 15 kilometers is probably a bit maybe obsolete. Current constraints are pushing that 15 down to maybe 13 or so. But it's still a fairly wide range of uncertainties. Okay. So why do we care what happens, what size of a neutron star would be? So one of the reasons is that neutron stars are interesting probes of dense matter. So here's sort of a phase diagram of the ground state of nuclear matter, the ground state, the lowest energy configuration at any particular basically net density or temperature. And so here in our sort of day-to-day lives, the lowest density or the lowest energy form of a thing would be an iron nucleus. If you have things like a heavy ion collider, you can smash things together and you get higher densities and higher temperatures and start to see cool stuff happening with transitions to quark and gluon dominated matter. The interesting thing that neutron stars do is that they bring you to a significantly high density without this temperature. So they probe a region of the phase space that we can't access with any kind of collider experiment on Earth, because they remain cold effectively through most of their astrophysical lives. Now, of course, when they merge together, things heat up and they can move up into some region here, but it's again low temperature compared to the heavy ion collisions that we see in other places. So the idea of what I'm doing today is basically to treat colliding astrophysical neutron stars as an enormous scale heavy ion collider. Measure what happens from them with a gravitational wave, and use that to learn about properties of dense matter in a regime we can't probe on Earth. Okay. Yeah?
I see your figure credit.
Yes. Cold baryonic matter? No, I don't know. I actually don't remember. It's been a while since I pulled this figure out, so you'd have to look up that. It's some sort of collision measurement.
Because they want to go up to the height without getting so hot.
No. Actually, this is the fair right here. So, well, I don't know exactly. So, okay. Yeah, I should remember where you get some plot from somewhere cool a while ago, and you put the credit on, and then you forget entirely where it actually came from. Okay. So this is a bit about how exactly this dense matter properties come into the stuff we can see when we're looking at a macroscopic object. So on the left here, we characterize one of the leading the leading way to describe neutron star matter when it's in the ground state, when it's cold and inspiraling, is just talking about what pressure is produced at a given density of matter. So for example here, you can just sort of scale the pressure up in the interior of a neutron star, and these dots here were a range of candidate realistic equations of state that we're using as sort of inspiration for this work. And as a result, as you scale up the pressure for a given mass of neutron star, the radius increases. And you also have different properties like the maximum mass that can be supported and the range of radius as a function of mass. And these kinds of things that people talk about constraining astrophysically. So as an example, here are some X-ray burst constraints from astrophysics, where here are a bunch of regions, constraints in this mass radius plane coming from X-ray binary observations. And this led to these green and red regions for the pressure-density relationship inside of dense matter inside the stars. So you can take some actually fairly widely ranging types of measurements, so some measurements that are not strongly constraining, and put them together to actually start learning where astrophysically you have some constraint on your properties of dense matter. Okay. So how does this come into a neutron star binary? And the leading order way to think about how matter is going to affect a system of two neutron stars orbiting each other is to figure out what the tide that is raised on the neutron star will be. So neutron stars in a binary system, they experience some tides, and we can characterize them in terms of the size of the quadrupole deformation over the strength of the external tidal field that's raising that quadrupole deformation. So this is very closely related to the radius. It depends, the size of the quadrupole deformation depends on radius to the 5th power, but it's modified by something called the Love number, which is this parameter here that comes in and gives you the effects above just the radius. And you can see these effects in a Newtonian case. So here again, we have the Love number k determining the quadrupole moment q of a deformed body in the Newtonian case. And what this does is this q is going to give me a gravitational potential modification around the object that is deformed. So this is the particular kind of characteristic that's going to tell you things about how a satellite moves around a deformed body, or how two deformed bodies are going to affect each other's gravitation, how the deformation is going to affect the gravitational interaction of two deformed bodies. So this is something that you can do just with the moon and the Earth in this Newtonian case, but it's, you have a generalized way to calculate the k and r in a relativistic star, but otherwise the leading order effect on the potential is the same. And the same way that we relate the equation of state to the radius, you can relate the equation of state to this parameter of how much the star is deformed. And you see things like large pressures will give a star of the same mass will deform much more in a way that affects the gravitational potential around it. So this is the parameter that we're going to use to characterize the effect on a waveform. And you can do this exactly to leading order in a post-Newtonian framework. So if you're doing a post-Newtonian framework, a lot of the times what you do is you consider an energy balance equation. You have the binding energy of the stars, you have the gravitational wave luminosity, and the evolution of the binding energy is determined by how much luminosity there is at each separation or at each frequency. So when you have a deformation like this, some of the energy is lost to gravitational waves, some of the energy goes into deforming the stars. So that gives you a faster in-spiral with a deforming star than you would if the star did not take energy to deform itself. The tidal bulges also add a little bit to the gravitational luminosity because they give a coherent quadrupole with the orbital moment, quadrupole of the system, but that's not as big of an effect as this change in the energy. So you can find formally how this would contribute to a post-Newtonian waveform, and again, sort of translating from our range of equation of state effects to waveform effects, you see now that the larger pressures are translating to a system that is merging earlier and has this accumulation of extra phase as it approaches the merger. Later, I'm actually going to be writing this in terms of a variant, which is a dimensionless characteristic parameter. So instead of r to the fifth, we do r over m for the parameters of the neutron star to the fifth. Just because dimensionless things are easier to work with. Okay.
So,
Mm-hmm.
regarding those time, the tidal bulges, they only dissipate by decreasing gravitational wave, or they also dissipate in any other way?
So there's an effective dissipation because orbital energy is lost to going into the deformation.
Right, but its energy is still inside the neutron star.
Yeah. It contributes to the gravitational radiation, but not very much. So, so normally you have the amplitude of the gravitational waveform comes from the quadrupole moment of the system. When they're bulging, each individual one, its bulges are spinning around, tracking the quadrupole moment of the binary, so you have a little bit extra quadrupole moment there. No, so for this kind of thing, we can approximate neutron stars as zero viscosity on this time scale.
So the only loss is just gravitational wave?
Yes.
How do you know that there's no viscosity?
You can make estimates of how big the viscosity would be, and it's orders of magnitude too low to affect things on the time scale of this dynamic. Well, I don't know. I've never seen someone propose a viscosity for neutron stars that would be substantial enough to modify their orbits.
Nobody's got a solution of why it's able to be higher, but it just is, right? It's just even as a free parameter and dial it up, right?
Right.
That affects the outcome of the potential, or other way around. Could we use this to measure the viscosity?
Well, you could. I probably use this to constrain the viscosity, but not very excitingly, unless we're thinking it might be 8 orders of magnitude off to begin with, I guess. So yeah, I can send you to some of the references people used for these estimates. There are the influence of neutron star viscosity does come into some other astrophysical observations, so there may very well be some other constraints that I'm not as familiar with that say it's below some value. They come into some resonance things or spin down, I think, properties of neutron stars. So, but, well, for now I'll assume there's 0 viscosity. Okay. Okay. So when we're talking about the contribution to the gravitational waveform, we talk about the waveform in the frequency domain, and we talk about the phase as a function of frequency. And if we break this is sort of the most important thing for measurement in a gravitational wave. And so breaking this sort of formula apart, things that the gravitational wave depends on, we have sort of shifts in the reference time and the reference phase. We have the leading order gravitational wave phase evolution that's coming from this energy balance. We have post-Newtonian contributions where the frequency is descaling with the mass and the redshift in a coupled thing. So this is why people will say that GR is scale-free. So if I do everything that I've talked about with post-Newtonian descriptions of the waveform, I can scale the mass or the redshift freely without breaking any of my modeling. The contribution of matter scales here with this parameter proportional to mass to the 5th power. And sort of a nifty implication that I'm not going to talk about is that this implies that if we know the matter effects, we could use this to constrain the redshift. It breaks the degeneracy of the mass redshift parameter pair for an in-spiral waveform. So if you're interested in sort of that, it turns out that this is not something that's going to be very useful for any of the detectors currently being built, but it's sort of something that might be interesting, 30 years from now. Okay.
It's not interesting right now because the detectors do not measure mass well enough, or because the persistent forces are just too slow?
So the sources are close enough that this is a few % change, and the accuracy to which we are measuring this parameter, which is sort of comparable to the accuracy that we're measuring the redshift, is much more than a few %. So this is currently obscured. Plus, we actually don't know what this should be, so we can't decouple it from the redshift anyway. Actually, instead, we should probably be worrying about how our equation of state measurement might get slightly obscured by the redshift buffeting things around. But anyway, I won't talk about that either. Okay, so where does this matter in the waveform? So we can talk about where different effects contribute to the waveform evolution by talking about the frequency of our gravitational wave. So as the pair of stars orbits, they come together and their frequency increases. And you can talk about how in a typical gravitational wave measurement, you can accumulate what's called the signal-to-noise ratio and measure the mass parameters at a particular band of frequencies. So the information about the masses of the neutron stars in that phase evolution and the total magnitude of the signal that you accumulate is focused at this range below around 55 hertz. Here, the tidal contributions all come in at the high frequency. So they're coming in above around 400 hertz here. So if, for example, we look at the last couple seconds of an inspiral, so in the last couple of seconds, starting 2 seconds, the gravitational wave frequency is 100 hertz. The two stars are around 140 kilometers apart. They merge together, and here in the last 0.05 seconds of the full orbit, they're going from around 400 hertz to collision over the last 60 kilometers of spiraling in together. And if you take this and you put matter into it, this whole part has no effect, basically, at all. Here, it's only this last piece at the end where you have some small accumulation of effects that then grow larger and larger, and this dark region at the end is where you would need a numerical simulation to understand what's going on. So the upshot of this is that for the purposes of detection, we don't need to worry about the equation of state effects. So let me say a little bit about what that means and why we know that. Okay. So if we're talking about how well we can measure a signal and discriminate between two different signals, as someone who likes to talk about relativity, I have a geometric way to think about all this. So this is my picture of signal detection. So we have, and of course, this would really be some infinite dimensional parameter space, or at least one dimension per frequency bin that you'd want to consider, but I'm just going to use something I can draw on a flat screen. So this is what I have. I have some origin in my signal space where there's no signal, and then I have some families of signals that range in a parameter, an arbitrary parameter. So it could be mass or whatever. It's just one parameter for now. So when I have a true signal, something actually occurs, it lives on my family of signals with some parameter value, but the noise of the detector will buffet that around. And when I measure it, it will be pushed around somewhere in this noise, sort of, this is like a Gaussian fall off of likelihood or probability. We'll measure a signal somewhere off from its true parameter values. So we can characterize this. We know what the noise is, the scale of the noise is around our measured signal. So we can talk about how loud the signal was that we measured. And then we can then talk about what parameter is most likely. So loudness measured, we can take a particular signal and say that if this is the amplitude of my gravitational wave signal as a function of frequency, so it comes in spirals through and merges somewhere up here, I can compare it to the amplitude of noise in my detector, so how much at each frequency the detector has some random motions caused by thermal effects or photon counting or seismic noise leaking into the thing and causing some fluctuations. And I can say when the amplitude of my signal is higher than the amplitude of my noise. So this is a particular signal, binary at 100 megaparsecs, which is a signal-to-noise ratio of about 3 in the early LIGO detectors, but in the design advanced LIGO would have an SNR of about 30. 3 is not good enough for detection because we take many trials over many possible parameters and many possible times when we do this kind of measurement. But 30, it would be one of the loudest signals we expect to see. Or we reasonably expect to see. So the next part of this is comparing, well, what the true parameter was to what the best fit of my parameter, or my parameter family of signals is to the thing I measured. So the noise has buffeted it around a bit, but I'm going to take the shortest path connecting it to my family of signals, and that will be the best fit parameter for the thing I'm trying to measure. If I want to see how well I can measure something, I want to see how wide the distribution of noise is compared to my waveform family. So I'm going to get some best fit noise, and I'm going to get some estimate for how much of my error is when I try and measure this. So I can talk about parameter space in terms of I can talk about parameter estimation in terms of distances between signals. So I'm going to talk about my signal to noise ratio giving me a characteristic distance in the parameter space that's the length of a gravitational wave signal, or it's a length for the gravitational wave signal away from my origin. Then what I want to talk about is the difference between two waveforms. The distance in that space of signals is going to be equal to 1, so the same scale as the noise, for something that is marginally distinguishable. And then we would say the expected measurement uncertainty for my parameter would be the change in parameter between these two waveforms that are marginally distinguishable. So one thing that you can do to estimate how well you're going to be able to measure something is to linearize around a particular parameter value. So if your parameter is, the change in parameter is small, you can write the waveform as the value it has at one parameter value, and then linearize around that and just multiply the change in the waveform by the amount of change in your parameter. And this is the basis of something called a Fisher matrix estimate for parameter measurability. So in this case, this criteria is equal to a 1 sigma bound with the Fisher matrix estimate. So with this kind of estimate, we can confirm two things. So the first thing we can see is that if we take our model below around 400 hertz, we see basically no impact from tidal effects, which is good because this is what we would use to detect signals, and we don't want a whole nother parameter to be worrying about when we're trying to figure out what if we saw anything. And you can also use this kind of thing for some tests of GR, but it confirms that up to around 400 hertz, tidal effects are not going to be significant in the detector. However, if you extend our model of the post-Newtonian effects to the point where the stars collide, then what you have here, so this is rho equals 16, that's half the loudness that I was talking about earlier. We have tidal parameters that are larger than the 1 sigma measurement error for a signal that is not especially strong. So this was some work done by De Moor, Nagar, and Villain that used the idea that EOB models of tidal effects have the same magnitude as post-Newtonian, and then this calculation was done using post-Newtonian tidal effects. One thing they did was they took an estimate of the contact from the radius of the neutron stars and just extended the post-Newtonian model right up to that point. But they also marginalize over things like uncertainties in mass, spin, and mass ratio that would possibly confuse these effects. Okay, so that's all good for linear parameter estimation. One thing you want to consider, though, is that this linear approximation does not always hold. So a weaker signal would mean that the noise is relatively larger, and there's no guarantee that the waveform family is linear in our space of signals. So for example, something at an SNR of 10 might give me an estimate of the parameter measurement of around 1, but if I have a half as loud signal, so the noise is comparatively twice as large, I might have more than twice the measurement error. Okay. So you have to be a little cautious when taking a linear thing, because the distinguishability in the measurement error may not scale linearly. So your Fisher matrix measurement can break down.
So in this example, your measurement error actually go more than you would have expected.
Yes.
Is it always going to get worse, or is it sometimes better?
I don't know of any mathematical argument for why it couldn't get better, but everything I've seen in practice has it getting worse. So maybe you could say something about, yeah. So
in practical terms, Fisher matrix estimates, are they too optimistic?
They can often be. Okay. So to get around that, this is an example of a movie showing the kind of parameter estimation pipelines that are actually used from the University of Birmingham. And you want to do something where, whoops, okay. You want to do something where you're doing more than a linear perturbation. You're actually doing a Markov chain Monte Carlo comparison of all the possible parameter values and finding the most likely values in a multi-dimensional parameter space, and it's all very nice and more rigorous than just this linear thing. And one of the things that you can then see if you do this kind of analysis, so there's a couple of results that have come out in the last year or so. So the first was a full Bayesian analysis where for multiple measurements of neutron star systems, you find that, well, one typical expected measurement won't be loud enough to pull out a parameter estimation on its own. If you combine many events, you can find a characteristic parameter describing the equation of state that becomes interestingly different for different equations of state at around 40 events, which is nice because 40 events per year is one of the typical predictions of how many binary neutron stars advanced LIGO would expect to see. So if you get 40 events per year, then you should start being able to say something about which equation of state characterizes the neutron stars. So this is nice because this is actually a full Bayesian analysis. It's including all the obscuration that other parameters could give you. The caveat, though, is this is using a post-Newtonian in-spiral, and it's extrapolating it up to high frequency. There's another paper that just came out last month by Les Wade and collaborators. And here we have something similar to the mass radius plot using effective binary parameters. So the chirp mass of the binary and some parameter that comes from the effective radius of a combined system of two neutron stars. And you see that here a single measurement gets you a range of radii, effective radii, that allows you to discriminate between different equations of state in a way that is comparable to the thing that you got extrapolating up to with a Fisher matrix. Okay. So what this is saying is for an injected signal with SNR 32, you get something that's agreeing with your Fisher matrix estimate, so that's nice. And even if you don't have a full SNR 32 signal, it looks like you can add up a bunch of signals and get something that's useful. However, there's a major caveat on everything so far, and that's that the systematic error is very significant in these post-Newtonian models. So there's a couple things that have come out also recently, basically saying that if we ignore the high post-Newtonian terms of the test mass, their effects are comparable to the size of these tidal effects that we're trying to measure. So it's things that we don't know are comparable to the effects that we're trying to measure. There's a similar Yagi-Yunus result where they ignored post-Newtonian terms of various orders and showed that the error from choosing the estimate of the post-Newtonian error is larger than the effect of tidal contributions. And this paper by Les Wade shows this too, where here is the parameter, the lambda parameter that you inject, and what you recover depends very much on the family, the post-Newtonian approximate that you use to recover it. Okay. So sorry. Huh?
I have a question about the previous slide. Why did you first finish that slide and then you can go back to it?
Oh, so I was just going to, so the choice of the post-Newtonian approximate, the error in the post-Newtonian model is going to obscure tidal effects if you just try and use it as is. Okay, so.
In Yagi-Yunus,
Mhm.
how do they estimate post-Newtonian terms that are known?
So, how did they? I forget right now exactly how they did that, but it was something. So it wasn't. So Favada did it with a test mass limit. Yagi and Yunus, I think they extrapolated somehow, but I don't recall right now exactly how they did it.
Why are people still using post-Newtonian?
There isn't anything else for tides, for neutron stars.
But can't you patch tides onto a numerical?
That will be like my awesome thing that I do in the next half of the talk.
Sorry.
Yeah. Okay. So, how do we get around this? Okay. So what we want to do is we want to do some numerical simulation to try and do better than this. Now, so there's two parts to this. There's looking at the in-spiral and the merger. And so I'll just flash through, because I'm sort of going slower than I expected. When should I wrap up exactly?
You've got lots of questions, so you have an hour.
From
When we started.
which, okay, so say 4:15 then, or 4:10? Okay. 4:10, I can do that. Okay, so what you can do is, so this is sort of the time of evolution. Here's some sort of phase as error in your simulations. And in the last while, there's been a bunch of simulations of binary neutron stars, comparing them to different post-Newtonian models, and seeing that, for example, post-Newtonian with tidal does a little bit better than post-Newtonian alone. When you do some various treatments of error and extrapolating it and things like that, which have many exciting details that I'm not going to talk about. So let me just say at least my interpretation of what this is telling us so far, and that's that the numerical simulation in spirals don't conflict with the post-Newtonian, but they're not accurate enough to actually measure the post-Newtonian. So they can't tell us anything beyond what we already, they can't really tell us more than we already know about the post-Newtonian for binary neutron stars, because it's challenging to do these simulations accurately. What they do show is that post-Newtonian does break down around 500 M before merger. And they also show that if you take various kinds of post-Newtonian approximate or effective one-body approximate, they are comparably effective in the region before everything breaks down. But that's all that they can tell us so far. So until SPEC gets some really highly accurate binary neutron star simulations out, we'll just have to skip on that and talk about what happens at the merger. Okay. So I'm going to show just two. Actually, let me just start these at the same time. They're not playing at the same rate, so don't read too much into the simultaneity here. But if you have large neutron stars and small neutron stars, you see that in the numerical simulations after the post-Newtonian breaks down, you do have some comparable effect where the large neutron stars will deform more and merge earlier, and then the compact neutron stars merge a little later, which you can see more by comparing their time of merger on this plot. There's also other exciting stuff that happens in the post-merger, where the large neutron stars, the higher pressure ones, support what's called a hypermassive remnant that gives off gravitational radiation after the two stars collide for some period of time. But I'm going to mostly be focusing on what happens before here for my talk about measuring the equation of state. So here's what we have. We have this amplitude of the gravitational waveform as a function of frequency, something that comes in and is effectively point particle around up to 400 or 500 hertz. And I'm going to compare it with what would happen if we had black holes of this mass, in which case they would continue on and merge at their quasi-normal ring-down frequency somewhere up here. If we have instead neutron stars, everything happens at a bit lower frequency because they're larger. So we have something like this, where we have an in-spiral with tidal effects dipping in well before the black holes started showing significant differences from the post-Newtonian. It merges at an earlier frequency, and here's all this post-merger oscillation stuff. And this sounds like this. Okay. If we change the equation of state, make the neutron stars larger, everything again moves to lower frequency, including the sound. So let me play that again because I like the sounds. Nope. Okay. So you can kind of hear from the different frequencies at the end of the in-spiral which one happened. And another mysterious and interesting thing is that the in-spiral parameter that I've talked about characterizes this merger frequency. This is not obvious that this would be in any way expected, but empirically we find this relationship where actually this lambda parameter, better than the radius, characterizes the frequency of the merger. So this is an appropriately weighted radius, effectively. You could say something like that. So this is useful, though, because it says that the merger characteristics of these waveforms could be used to constrain the same properties as the tidal stuff that was happening at earlier frequencies. So I'm going to do this in two ways. The first way has the advantage that it's going to sidestep all the post-Newtonian errors entirely, and that's just taking pure numerical templates for my waveforms. Okay, so I'm just going to take the numerical templates. I'm truncating the post-merger because there's all sorts of other stuff happening there besides the equation of state that's going to affect what happens. So I'm just going to take the numerical simulations over the last dozen or so cycles from around actually 600 hertz to the point where the stars collide, but not when they're forming any post-merger oscillations. I'm going to skip over how we actually calculate the significance of the waveform differences, but this is this h1 minus h2 distance in parameter space that I talked about earlier. And we see, for example, that at 100 megaparsecs, our 1 sigma error is going to be at, say, 300 in this particular parameter. But at half the distance, at twice the distance, where we have half the error, we get a parameter difference of 2,000 at 200 megaparsecs. So this is exactly this nonlinear scaling that we were worried about before. As the signals get weaker, the ability to measure parameters gets worse faster. So if we put back into mass radius plots, these two would be distinguishable at 100 megaparsecs, but we would only be able to distinguish these two at 200 megaparsecs. And this one is sort of unrealistically large, so that's less interesting, although it's not totally uninteresting. So we would need a pretty loud signal, something that's around 30 SNR, to be able to say something interesting about two different equations of state. One thing that we do want to talk about, though, is the systematic error. So if our model waveform family doesn't actually align with our true waveform family in the parameter space, I might be trying to find the best model waveform that fits a true waveform and have it be shifted in parameters. Okay? So here's the true parameter value and the true waveform, but the closest model waveform can be shifted in parameters. So if I try and do a best fit parameter value, I'm going to get something wrong because my model waveform family isn't the right one. So we're going to characterize the size of this by a systematic error on the parameter value. And you can explicitly estimate this, and the upshot is that you want to compare the distance between two different waveforms of the same parameter value, this is a systematic difference, to the difference between waveforms of differing parameter value, and ideally you're going to have a good measurement if this is large and this is small. So here we can estimate the systematic error by looking at the differences between the same parameter and different simulations. And so, for example, for these simulations, we have a non-trivial, non-negligible systematic error. It's around 40% at 100 megaparsecs, 20% at 200 megaparsecs. These are not cutting-edge simulations. They're simulations that differ by 0.1 to 0.3 radians over the last 1,000 im of the simulation. Yeah?
When you say different simulation, is it different resolution, or is it different equation of state which has the same parameter?
These are the same equation of state, different resolution, and two different codes.
Oh, it's different codes?
Yes. So there's, yeah, whiskey and Sacra. Yeah. So we have to be a bit cautious about what we say because there's some error even in our numerical templates that can be large comparable to this. This isn't, however, larger, which it would be in these systematic p-n only estimates. And the other thing that we want to do is create hybrid waveforms, where we take some post-Newtonian model and match the numerical simulation data onto it into this hybrid waveform. So here I have frequency as a function of time. As the waveform chirps up, at some point the numerical simulation departs from the post-Newtonian model, and I'm going to match those together and use that to estimate my parameter value. Now, I guess I should say that with the accuracy of the numerical simulations, we can't do better than post-Newtonian in the in-spiral much yet. So we have to be taking something, they basically can be made to agree in this intermediate region. So this does still suffer from the systematic errors that daunt the post-Newtonian waveforms. That's another hybrid. Okay. But the thing that this gives us is a difference between waveforms which has a delta lambda of 500 at 400 megaparsecs, which is pretty much the same that we got with the p-n plus tidal estimate. So here I vary my parameter value by some amount. I see this change in the waveform. I can see this out to 400 megaparsecs. So this is cool because that's almost as far as we can see anything with advanced LIGO. So this would be very exciting if we could get it to work, because it gives us two different equations of state that are plausible astrophysically, that are distinguishable at 300 megaparsecs, and the magnitude of our hybrid estimate agrees with the magnitude of the PN estimates. So all these cool things that I showed before would work if we could use real waveforms in them, our best guess of real waveforms. But the systematic error is large. Okay, so here the systematic error just from hybrid construction is almost as big as the statistical error on the parameter to begin with. Here it's coming from other variations than those I've shown on the plot. So changing the matching region and changing the way this match is done. The interesting thing, okay.
Sorry for my slowness here. Could you remind me again which points I need to compare with each other to get the systematic error?
That's why they said this includes some comparisons that aren't on this plot. So, yeah.
Just the numerical simulation, is that too short in that comparison properly?
Not accurate enough for long enough. Yeah. So, yeah. They can be long simulations, but if they're not accurate enough, they don't actually help in any way.
So you can only use like that.
Yeah, it turns out you do better if you ignore most of the numerical simulation, which was really, really kind of depressing after doing all this work to simulate things. But so this is actually an open problem. I don't have a conclusion that's better than this. I do want to spend about 5 minutes talking about some of the things that we're trying that may be able to do better. One thing this does do is that, actually let me go on here. This does, the differences between P and approximates gets worse and worse as you go up to these high frequencies. So this does cut off some of the places where your different P and approximates are disagreeing with each other and contributing systematic errors. But I think it probably gets you back almost as much from the hybrid matching issues. Okay. So one thing that you may notice, this was seen both in the spiral simulations and in our best work on hybrids, is that we have numerical simulations that are systematically merging earlier than our best P-n approximate. This is a P-n approximate which includes the tidal contributions, and that would agree very well with a binary black hole at the same time and frequency range. So one of the things that I'm working on right now is trying to figure out a way to better fit this merger region of the binary neutron stars. And the inspiration actually comes from a 1995 paper on tidal resonance effects at the end of the merger by Cockadis and Schaefer, which shows that if you add resonances, so this is a different kind of tidal effect. This is the tidal forcing frequency couples to a natural mode of the neutron star at the end of the orbit. And this gives you something that looks similar to what we were seeing in the numerical simulations. Okay, so this is a time, this is a frequency, and you see that with the resonances, they're merging earlier than without. So we tried to put this, so a master's student at Fullerton put these contributions, the energy transferred directly into the tidal forcing. This is a real effect we expect to be there, and it does change the phase evolution at the end, but only a little bit. But the interesting thing is this little bit of phase evolution does entirely change the spectrum that we predict to see from this kind of merger. So again, this is the black hole. This would be just a pure post-Newtonian, I think Taylor T4 amplitude. Here's Pn plus tidal, adds this correction here. Here's Pn plus tidal plus resonances. So we actually have something at an interesting frequency range that is changing our waveform model, even though the phase differences aren't too big. Okay, and then, so we're hoping to use this as a basis for a phenomenological merger. So we just put in the F mode of the star. That doesn't work very precisely, but in general, you can see there's some work done analyzing the post-merger, that the merger to, the transition from M-spiral to merger is well modeled by the onset of a resonance of the two-star system as a whole. So if you look, at, let's see, oops. If you look at this, you can think of it as the in-spiral happens faster because energy is being transferred to these modes here where the post-merger system is giving off gravitational radiation at these frequencies. So we think we can empirically fit the frequency of our resonance to improve the model that we have for merger of binary neutron stars. And I think I'll skip that and just wrap up. So the outlook is that the equation of states are large enough to be measurable with our reasonable guesses for rates and things like that, of course, if we have accurate waveforms. But currently, the systematic errors are large, especially for PN plus tidal models. They're not sufficient to use to measure these parameters. One thing we can do is try and sidestep that by using numerical simulations as templates. That requires some sort of phenomenology to even cover the parameter space. But we could get a significant improvement in how well we can measure things if we had a trustable hybrid waveform, which we don't, but we should be trying to work as hard as we can to find one. So I'll stop there. Thank you very much.
So we do actually have time for one or two quick questions before the time. Any further questions?
Harold's from the COOP. What's the biggest limitation of the numerical waveforms now? I mean, the treatment with hydro, or? I'm just looking around here because the people who read it.
Yes, so in for most codes, the law or the method used both for mostly for the aerodynamics, which is in general second order accurate only, and which tend to accumulate too much error, even for moderately short waveform close to merger. There is work by David Radice and Jocelyn Reed on higher order methods, which are likely to improve this in the long term. But getting both the higher accuracy and long enough waveforms to hybridize them early enough that it actually gets rid of all those PN issues is a problem. Even in black holes, getting waveforms long enough to get rid of all the PN issues has been a problem. And all waveforms are 3 to 5 times shorter.
So, I mean, there is like so I showed sort of the sidestep with the numerical simulations only. If we have longer and longer numerical simulations, we will do better and better at that. So, you know, a sufficiently long numerical simulation will approach the full hybrid.
So you need to lengthen the numerical simulations in terms of the pre-in-spiral reaction by about 3 to 5.
No, because those effects are only important close to merger. I think we probably don't need 50 orbits to get to the entire effects.
Well, what?
No, I'm talking about the hybridization.
Yeah, so the hybrid. So the issue is you need why the numerical simulations only are less accurate is you kind of need a lot of low frequency cycles to anchor the thing enough that it can detect subtle phase accumulation at the high frequency. So if you only have a short numerical waveform, you marginalize over shifts in phase and you obscure these smaller effects. So having an accurate, trusted simulation of the in-spiral where you don't expect the numerical, the tidal effects to be very significant is still useful in giving you a different kind of, you don't have the same systematic error. You have different systematic error.
I'm just not sure how people do this kind of tidal model. If it's, only if the tide is only sort of bending down by gravitational wave radiation, it's not going to bend down fast enough. That may still be back reaction onto the orbit. And also when you pass through resonances, how you pass through it, how quickly you pass through it, all this kind of thing. I'm still actually running hands on.
So let's see. So the resonance I talked about is actually formally after the merger. So they're not passing through it, they're approaching it, and that drives the earlier approach to merger. In general, people have done estimates for the energy transfer as the neutron stars pass through resonances, and that is not large enough to have significant waveform effects. So one of the things is the orbital energy of these stars is so huge that they can give off, they can pump 10 to the 46 ergs into something happening on, and it makes absolutely no difference to the orbital evolution.
So when you say tidal model, you just mean deformation?
In here, yes, this is just a linear deformation of the stars as predicted by an induced tide.